Problem number 1. A magazine provided results from a poll of 539 adults who were asked to identify their favorite pie. Among the respondents, 25% chose chocolate pie. If the confidence level is 84%, use the walled asymptotic method with continuity correction to calculate the confidence interval for the proportion of adults who identify chocolate pie as their favorite pie. Show that the normal approximation to the binomial distribution is applicable. Use the normal table and linear interpolation to determine the critical value. Enter the upper bound of the confidence interval as a percentage without the percent sign. Round your percentage to the nearest tenth. So let me do that. So I have that the sample size was 539. Success was that they preferred chocolate pie. And so the sample proportion of successes was 0.25. We want to determine the 84% confidence interval for estimating my true population proportion. So first, in order for us to use the walled asymptotic method, I have to show that it is applicable. So let's show that the normal approximation to the binomial distribution, this is a binomial distribution, is applicable. So let's do n times p. So 539 times 0.25, 134.75, that's greater than 5. N times q, 539 times. If you have a 25% chance of success, you have a 75% chance of failure, 404.25. That's again greater than or equal to 5. Therefore, since both of these are greater than or equal to 5, yes, the normal approximation to the binomial distribution is applicable. So we can, so the normal approximation is applicable. So now let me try to determine my critical value. So now I know that the sampling distribution can be approximated by a z distribution. So I'll find the critical z value. Well, 0.84 divided by 2 is 0.4200, which is between 0.4192 and 0.4207 at 1.40 and 1.41. And so I have here the following. I'll just rewrite what I had from the table. So let's use linear interpolation. So z is equal to 1.4 plus 1.41 minus 1.4 divided by 0.4207 minus 4192 times the quantity for 0.42 minus 0.4192. And so z is 1.4 plus 1.41 minus 1.4 divided by 0.4207 minus 0.4192 times 0.42 minus 0.4192. So you get that z is equal to 1.40533. So for the walled estimate with continuity correction, my error is just the z, 1.40533, times the square root of p, 0.25, q, 0.75 over n, 539, plus 1 over 2 times n, 539. And so you get that the error is equal to 0.027138761. And so my confidence interval is the sample proportion, 0.25, plus or minus my error, 0.027187651. And so if I subtract these, I get 0.222812349. And if I add these, I get 0.277138761. And so my upper confidence level is 27.7%. Problem number 2. You are an operations manager for an airline, and you are considering a higher fare level for passengers in aisle seats. How many randomly selected air passenger must you survey? Assume that you want to be 95% confident that the sample percentage is within 2.7 percentage points of the true population percentage. So N is just equal to Z squared PQ over E squared. Well, for a 95% confidence interval, you can either look it up or you've used it so many times, you've memorized that Z is 1.96. E is, well, 2.7%, so 0.027. P and Q, I don't have any estimates for P and Q. So in this problem here, they give us no estimates for P or Q. Therefore, since we do not have any estimate of P or Q, we use the largest maximum, which is 0.5. So let's use 0.5 for both P and Q. And so N is equal to 1.96 squared times 0.5 times 0.5 divided by 0.027 squared, 1,317.421125. And you round this up to 1,318. So that's your sample size. 3. Salaries of 25 college graduates who took a statistics course in college have a mean of $87,666, 87668, and a standard deviation of 1574. Construct a 95% confidence interval for estimating the population mean. Enter the upper bound of the confidence interval. Round your answer to the nearest whole dollar. So in this case, N is 25. The sample mean is 87668, and the sample standard deviation is 1574. I do not know my population variance. Therefore, I'm going to have to use a t-distribution. I will be using a t-distribution. And so I need to know my degrees of freedom. 25 minus 1 is 24. So my degrees of freedom are 24. And I can look that up. So we have a 95% confidence interval. Confidence intervals are always two-tailed. So I'm going to look at two-tailed. If 95% is in the middle, then the total in the two tails is 5%. So look at 5%. I'm using a Z distribution. So I go my degrees of freedom are 24. And so I go and I look at 24. And so my critical value is 2.064. So my confidence interval is the sample mean plus or minus my error, which is the t critical value times your standard deviation for the sampling distribution of all possible sample means. which is just the, since we're assuming a infinite population, which is just the population standard deviation divided by the square root of the sample size. So we have here that T is 2.064. I don't know the population standard deviation, but I can approximate it by the sample standard deviation. 1574 divided by the square root of n, 25. So I get that my error is 649.7472. And so my confidence interval is 87,668 plus or minus 649.7472. So if you subtract, you get 87.87018.2528. And for the if you add, you get 88,317.7472. So rounding to the nearest dollar, I get that the confidence interval is from 87,018 to 88,318. And so my upper limit for my confidence interval is 88,318. 4. Salaries of 25 college graduates who took a statistics course in college have a mean of 89226 and a standard deviation of 1522. Construct a 99% confidence interval for estimating the population variance. Enter the upper bound of the confidence interval. Round your answer to the nearest whole number. So in this case, n is 25. I'm going to be using a chi-squared distribution. So my degrees of freedom, 25 minus 1 is 24. Let's find the critical values for my chi-squared distribution. So this is a 99% confidence interval. So two-tailed, a total of 1%. And so I have, maybe I should draw this. I have here a 99% confidence interval. So that says here that 1% total is in these two tails. Therefore, for each of these tails, we have half, 0.005. My degree of freedom is 24. So I have that my right tail is 0.005, and my degree of freedom is 24. And so my critical value is 45.559. Now, this is in the first column. Therefore, the other value also 9.886. And so those are my critical values, 9.886 and 45.559. My confidence interval for variance is that the population variance is between the degree of freedom times the sample variance over my, right and left chi-square critical values. So let's figure out each of these. The degree of freedom is 24. My sample standard deviation was 1522. So square that to get the population, the sample variance, and then divide by each of these critical numbers. So the 45.559 and the 9.886. So if you do that, you get sigma squared is between 1,220,299.304 and 5,623 671.455. So let's round this to the nearest whole number. And so if you do that, you get 1,220,299 to 5,623,671. So the upper limit is going to be the 5,623,671. Okay. Problem number 7. John wishes to estimate the population standard deviation of the salaries for college graduates who took a statistics course in college. How many college graduates must he survey? Assume he wants to be 99% confident that his estimate of the sample standard deviation is within 40% of the true population standard deviation. So he wants to be 99. So we're estimating the standard deviation and we want to be 99% confident. So we're estimating the population standard deviation and we want to be 99% confident. So we'll be using this column here. And we want to estimate the standard deviation within 40% of the true population standard deviation. Problem 6, a simple random sample of men who regularly work out at Mitch's gym is obtained and their resting pulse rates in beats per minute are listed below. Use a 0.05 significance level to test the claim that these sample pulse rates come from a population with a mean less than 72%. Oops. Wait a second. Oh, yes. Will this recording be, if you send me your email, then if you email me, and let me put my email in the chat, then I will email you I'll email you the recording, yes, and the PDF. So I'm putting in there. So I put in my email for you guys. Okay. Let me, 1 second. I'm a mute.
You are muted, Professor. You are muted.
Okay. Okay, so let me not do that. Thank you very much. Problem number 6. A simple random sample of men who regularly work out at Mitch's gym is obtained and their resting pulse rates in beats per minute are listed below. Use a 0.5 significance level to test the claim that these sample pulse rates come from a population with a mean less than 72 beats per minute, the mean resting pulse rate for men. Assume that the standard deviation of the resting pulse rates of all men who work out at Mitch's gym is known to be 8 beats per minute. Use the critical value method of testing hypotheses. So we have here 75, 64, 57, 78, 77, 51, 69, 51, 75, 66, 65, 60. Enter the test statistic, round your answer to the nearest hundredth. So we want to test that the mean is less than 72. And so the alternative hypothesis is that the population mean is less than 72. The opposite of that, the complement of this, is the null hypothesis, that the mean is greater than or equal to 72. And let alpha equal 0.05. We're given that the population standard deviation is 8. So we're given the population standard deviation. So this is going to be, well, a left-tailed z-test, because we know the population variance. Let me determine some of the statistics. So the sample mean, let's add up all these numbers, divide by how many there are. So if you add them all up, you get 788 divided by 12. And so 65.666. Let's find the critical value. So this is, z 0.05. And so this is one-tailed, 0.05. And so I have here a negative 1.645. This is left-tailed. And so this is so alpha here is 0.05. This is a left-tailed test. And so this is my rejection region for values of z less than negative 1.645. Let's find the parameter for my sampling distribution. The mean for the sampling distribution of all possible sample means is the mean of the population, which by the null hypothesis is assumed to equal 72. The standard deviation for the sampling distribution of the difference of these two sample means is equal to, well, the population standard deviation, which we were given as equaling 8, divided by the square root of the sample size, which is 12. And so I get that this is equal to 2.309401077. So let's calculate my test statistic. And so z is x minus mu over sigma. So the sample mean, we just calculated that. 65.6 minus 2 over sigma 2.74241379. Well, this is in the rejection region. So since the test statistic is in the rejection region, then I reject the null hypothesis. So yes, there is insufficient statistical evidence to reject the claim that these sample pulse rates came from a population with a mean of less than 72 beats per minute, the mean resting pulse rate for men. Oh, I just repeated that the test statistic rounded to the nearest hundredth was a negative 2.74. 7. A manufacturer uses a new procedure. A manufacturer uses a new production method to produce steel rods. A random sample of 14 steel rods resulted in lengths with a standard deviation of 3.81 centimeters. At the 0.01 significance level, using the p-value method, test the claim that the new production method has lengths with the standard deviation different from 3.59 centimeters, which was the standard deviation for the old method. Use the normal table and linear interpolation to determine the p-value. Okay, so we want to test here that the standard deviation is, that the standard deviation is 3.59. Well, is not equal to 3.59. So we don't really test claims about standard deviations. We test claims about variances. So let's square the standard deviation, 3.59, 12.8881, and do the claim about this. So it's saying that they want the standard deviation to be different than 3.59. So the alternative hypothesis is that the population variance is not equal to 12.8881. And well, looking at its complement, the alternative, the null hypothesis, is that sigma squared is equal to 12.8881. Let alpha equal 0.01. So in this case, well, n is 14. We're going to have to be looking at chi-squared. And so I have to figure out my degrees of freedom. And so 14 minus 1 is 13. And we have that the sample standard deviation, here it is, oops, is 3.81. Let's calculate our test statistic. So chi-squared equaling degrees of freedom, 13, times the sample standard deviation squared, so 3.81 squared, divided by the population standard deviation, population variance, which is 12.8881. And so let's calculate. So I get chi-squared is 14.64213499. So let's calculate my p-value. Well, this is for a two-tailed test. And so I have that the p-value is the probability that chi-squared is not equal to this 14.64213499. So to actually do this for a two-tailed test, I'll figure out the probability that chi-squared is greater than 14. This is in the right tail. And that chi-squared here is greater than 14.64213499, and then I'll double it. The reason that we know that this is in the right tail is because the 3.81 is greater than the 3.59. Okay, so I want to calculate this. Well, I could plug it onto my TI-84, but they tell us that they want us to use the Wilson-Hefferty approximation. No, they don't. I could plug this into my calculator. I could plug this into, yeah, I could have done. It's because later on I do it on my calculator. So I want to show you at least how to do this using the Wilson-Hefferty approximation. So Z is equal to, so let's try to figure out, let's try to rewrite this instead of in terms of chi-squared, in terms of Z. And so I have that Z is equal to the cube root of chi-squared, 14.64213499, divided by my degrees of freedom, 13. Yeah. minus 1 minus 2 over 9 degrees of freedom 13 divided by the square root of 2 over 9 times my degree of freedom 13. And so I have that z is equal to 0.4401112831. So my p-value is twice the probability that z is greater than the 0.4401112831. So let's look at that, 0.44, and it's somewhere between 0.44 and 0.45. So 1700 and 1736. So 0.44 and 0.45, so 1700 and 1736. So let's figure out what the probability is. So P is equal to 7.17 plus 0.1736 minus divided by 0.45 minus 0.44 times 0.4401112831 minus 0.17. Okay. Minus 0.44. I said the wrong thing. Minus 0.44. And so you get 0.17004000619. But that just gives you the area between 0 and this value. So to find the area of the tail, let's subtract this from 0.5. So you get 0.3299599,381. And well, that gives you this. So I need to double it to find my p-value. So p is equal to, well, doubling this, 0.65999198761. And so let's round this because it tells us to round out, which is greater than 0.01 alpha. So P here is greater than alpha. So I do not reject the null hypothesis. So no, there is insufficient statistical evidence to support the claim that the new production method has lengths with a standard deviation different from the standard deviation for the old method. Let me do problem number 8. A medical school claims that less than 24% of its students plan to go into general practice. It is found that among a random sample of 50 of the school's students, 28% of them plan to go into general practice. Find the p-value for the exact test to support the school's claim. Round your answer to the nearest 10,000. Okay, so less than 24%. So the alternative hypothesis is that the population proportion is less than 0.24. Well, let's look at its complement. So the null hypothesis is that P is greater than or equal to 0.24, and alpha here is equal to 0.05. Well, let's see, N is equal to 50, and the sample proportion is 0.28. Okay, so let me rewrite this as, how many successes is that? That's 14 successes. So let me figure out the p-value here. Uh-oh. I just saw an error there. So let me calculate the p-value. Everything's still going to work. So let's calculate the p-value. So I have here, this is less than. So let's find the probability that x here is less than or equal to 14. So the sum arguing 0 to 14 of, well, this is 50 CR using the binomial formula, the binomial probability formula. So 50 CR times 0.24 to the R, 0.76 to the 50 minus R. So this is just binomes. I'm going to just do it on my calculator. Binom CDF 50, comma 0.24, comma 14. So let me do that on my calculator. And so here it is. So let me calculate. There it is. Second distributions. Go to binom CDF. Number of trials is 50. P is 0.24. And X is 14. CDF, good. And so I get 0.798 73 11 837. Okay. Yes, okay. And you want to round to the nearest 10 thousandths. So 0.7987. Well, I have that P here, 0.7987311 is greater than 0.05, quite a bit bigger. And so P is bigger than alpha. Therefore, you are not in the rejection region. So you do not, whoops. So you do not reject the null hypothesis. So no, there is insufficient statistical evidence to support the claim that less than 24% of the students at that medical school plan to go into general practice. Okay. 9. Interpret the 95% confidence interval for mean weekly salaries of shift managers at Giuseppe's Pizza and Pasta. Mu is between 325.80 and 472.30. So let me state it in the way that it was stated from the online choices. So of all the online choices, this was the best option to choose. If we obtain all simple random samples with replacement of size n of shift managers at Giuseppe's, oh no, this wasn't a multiple choice. So if we obtain, so this is where you're supposed to just type in the answer. If we obtain all simple random samples with replacement of size n of shift managers at Giuseppe's Pizza and Pasta. And we then construct confidence intervals for each of these samples. Then the true population mean will be contained in 95% of these constructed confidence intervals. The confidence interval mu between 325.80 and 472.30 is an example of such a constructed confidence interval. Problem number 10. An entomologist writes an article in a scientific journal which claims that fewer than 3 in 10,000 male fireflies are unable to produce light due to a genetic mutation. Assuming that a hypothesis test to support this claim has been conducted and that the conclusion is to reject the null hypothesis, state the conclusion in non-technical terms. So here, this was, I guess, a multiple choice. So this is the best of the results. There is sufficient statistical evidence to support the claim that fewer than 3 in 10,000 male fireflies are unable to produce light due to a genetic mutation. Okay. 11. A magazine provided results from a poll of 109 who were asked to identify their favorite pie. These people in the poll were chosen out of a population of 2,792 adults. Among the respondents, 44% chose chocolate pie. If the confidence level is 99%, use the Wilson score of asymptotic variance method with continuity correction to calculate the confidence interval for the proportion of adults who identify chocolate pie as their favorite pie, show that the normal approximation to the hypergeometric distribution is applicable. Use the normal table and linear interpolation to determine the critical value. Enter the upper bound of the confidence interval as a percentage without the percent sign. Round your percentage to the nearest tenth. Okay, so let's do this. So let's collect all the information. So the sample size was 109. The population size was 2792. And the sample portion was 0.44. And we want a 97% confidence interval. And so sample size is 109, population size 2792, the sample portion 0.44, and it's a 97% confidence interval. So first off, let's check if the normal approximation to this hypergeometric distribution is applicable. So let's look at n times p. 109 times 0.44, 47.96. Well, that's greater than equal to 5. Let's look at n times q. 109 times, well, if you have a 44% chance of success, you have a 56% chance of failure. So 61.04. So again, that's greater than equal to 5. So yes, the normal approximation is applicable. So we can actually calculate this using the Wilson score. So let's determine the critical value. And so let's do 9.97 divided by 2, 0.4850. So look for 0.4850. That is 2.17. So Z is 2.17. Let's calculate the Wilson score with continuity correction. So the Wilson score with continuity correction says that your confidence interval is Z squared big N minus little n plus 2 little n p plus or minus 1 times big N minus 1 plus or minus the square root of Z squared big N minus little n plus 2 times little n p plus or minus 1 times big N minus 1 quantity squared minus 4 little n times quantity big N minus 1 times quantity p plus or minus 1 over 2 little n quantity squared times quantity little n plus z squared quantity times n times big N minus little n times the quantity z squared plus 1, all divided by 2 times the quantity, well, little n plus z squared quantity times big N minus little n times the quantity z squared plus 1. Okay, so plug all that in. So z, wherever I see a z here, I replace z by 2.17. Well, that's what it's going for. It continues on. Okay, so unfortunately, this was kind of, when I plug it in, it was too long. So my numerator continues on over here. Then I say divided by a denominator. Okay, so I replace each of these z's here. 2, 4, 6 of them. 2, 5, 6 of them. Yes. So I replace all those by 2.16, capital N by the 2792. So each of these capital N's here. By 2792. Okay. All the little n's by 109. And let's see, that little n and this little n. Okay, so, oh, and p hat by 0.44. I selected the wrong line. P hat by 0.44. Oops. And this by 0.44. And that's it. Okay. And then you plug into your calculator. So you get 0.3389496231 if you subtract, and if you do the pluses instead. So if you do just the minuses for the e's, then that's what you get. So you're just picking these minuses here. If you do that, you get this. If you pick all the pluses, so make all these pluses here, then you get 0.546047727. And so this goes from 33.9% to 54.6%. So the upper limit is 54.6%. Now, This is kind of complicated to plug into your calculator. So this might be a good example where maybe you should program it in. And so maybe you should put in a little program here. We'll name it something. We'll then ask you to input p hat z, the sample size, lowercase n. Unfortunately, on the TI 83, 84, we can't do lowercase n's. So to distinguish it from the uppercase n, I'll just tell you, well, give me the sample size, and I'll call it something m. Give me the population size, and I'll call it something n. Then I will do, so this guy here, I'll make that I guess. See if I can. Oh, well, I can't quite show that, can I? Darn. So this guy here, which repeats more than once. So same as this guy. So notice that this guy here, the same as this guy here. And so there's a repeat. I'll call this A. And I guess I'll call it A when it has a minus sign. So it has a plus or minus. So I'll call this A when it has a minus sign, and I'll call it B when it has a plus sign. So that's all it's saying. So when it has a plus sign, I call it B. When it has a minus sign, I call it A. Next, let's call this guy here, which is the same as this guy here. Let's call this C. Then I just have an A here and a C here. So that makes my calculation a little easier. So this is A plus or minus. Well, in this case, it'll be a minus. A minus the square root of A squared, this, times C. And so A minus the square root of A squared, this guy that I couldn't really, I didn't make it into, I could have actually, no, I see, I'd have to repeat it twice, so it wouldn't be that big of a saving. So minus 4m, 4 little n times big N minus 1, then p minus 1 over 2n squared times that quantity we have for 4, all divided by 2 times it. Now, I'll do the same thing, but the only difference is that, well, B is when you have a plus. So this will become a plus. And this will become a plus. And so I replace all the A's here by B's, make this minus a plus, and this minus a plus. Then everything else repeat as being the same. I'll store that in L for the lower limit and U for the upper limit. And then I'll get these numbers. It'll be less prone to error if I do that. So let me input this in to my calculator. So let me switch over to show you how to do that. Let me put it on the TI 84 or 83. Okay, so let me go to Program, and let's go to New. And let's call it something. Wilson with hypergeometric with continuity correction. Okay, there. And click on Program yet again. And we'll get some options. Go use your arrow key to go to I/O, and the second one down, prompt. And we will prompt for Z. So let me input Z, so alpha Z, and do the same thing for, oh, well, I wanted P first. Not that it really matters, just because I said P first. And then we'll prompt for Z. And so again, program, I/O, the second one down, and we'll prompt for Z. Okay, next I want to display. So go to program, I/O. Display is the third one down. I want to display something. Let me lock my alpha key. So I'll do a second alpha, so I don't have to do all this. And let me put in quotation marks, sample size. And I will give a little space here, sample size. And let's unlock this. Let's go to math. Oops, test, sorry, second test. And the first one up there is an equal sign. And then I'll do alpha, and I'll close my thing. Maybe I should, no, that's good enough. Okay, so I'll display that. Now hit enter. Then I'll go to input. So I'll do program yet again, I/O, and input is the first one. And I'll say that I'll input this into M. Next, program, I/O, display, third one down. And let's lock my alpha. So let's put some quotations here, population size, population size. Oops. Spell it correctly. Not that it really matters. Population size. And let's unlock this. And let's go to test equal, because I like equal signs. And then let's end the quotation. And let's input this. So program, I/O, first one is input. And let's input this into N. Okay, so now let us parentheses 2MP minus 1. Oops. N minus 1. Let's store that in A. Let's do M plus Z squared and let's multiply that by N minus M Z squared plus 1. And let's store that in C. Then let's do 2MP plus 1 times N minus 1 plus Z squared. And let's multiply by N minus M. And let's store that in B. And lastly, let's do A minus the square root of a squared minus 4m n minus 1 p minus 1 divided by 2m squared divided by 2c. Let me just check really quickly. A minus, oops. I have a extra. I wrote that somehow incorrectly. Okay, a squared minus 4m n minus 1 p minus 1 over 2m squared. I forgot a c here. Okay. Okay, there. And I want to store that in, let's say L. Okay, and then next, B plus square root of B squared minus 4m n minus 1 p plus 1 over 2m squared c divided by 2c. Store in U. Okay, so that should be fine, hopefully. And let me quit. Okay, so okay, so 0.44, 2.17, 109, 2792. And so you get here, and if you look at L, the lower limit is 0.3389496231, and the upper limit is 0.5460477727. Okay. So there it is. Yes. Okay, so you can just use, well, once you input that in, then you can use that to do that somewhat lengthy calculation. Okay. Problem number 12. A marketing survey involves product recognition in New York and California. Of 71 New Yorkers surveyed, 15 knew the product, while 16 out of 34 Californians knew the product. At the 4% significance level, use the critical value method to test the claim that the recognition rates are the same in both states. Show that the normal approximation to the bivariate binomial variable is applicable. Use linear interpolation and the normal table to determine the approximate normal critical value. Use the Wald asymptotic estimate without continuity correction. Enter the test statistic, round your answer to the nearest hundredth. Okay, so let's do this. So we want to show that that the rates, well, that the percentages are the same. And so the null hypothesis is that the population proportion for New York minus the population proportion for California is 0. The alternative hypothesis is that P sub n y minus P sub c is not equal to 0. And alpha here is 0.04. Let us show that the normal approximation to these bivariate binomial variables is applicable. And so let's show that n times p. Let's look at n times p. So, well, n times p is, well, for New York, it's 15. Oops. For New York, it's 15, and for California, it's 16. And so n times p is 15 for New York. N times p is 16 for California. N times q, well, if 15 knew the product out of 71, then 56 did not know the product. And let's look at n times q for California. So 16 knew the product out of 34, then 18 did not. So for each of these, NP and NQ are all greater than 5. Therefore, the normal approximation is applicable. So let's try to determine the parameters that we'll be using for the Wald estimate. So the mean for the sampling distribution, the difference of these two sample proportions is the difference in the population proportions, which by the null hypothesis is assumed to be 0. Since the difference of these population proportions is 0, then I should pool the estimate. So I should use a pooled proportion. And so the pooled proportion is the sum of successes for New York and California, 15 plus 16, over the total number in New York and California, 71 plus 34. So 31 over 105. Therefore, the standard deviation for a sampling distribution of difference two sample proportions is the square root of, again, you estimate both the population proportion of successes for both New York and California by P bar, and you estimate the population proportion of failures for both New York and California by Q bar. And we'll factor out both P bar and Q bar. So it's the square root of P bar Q bar times 1 over the number of people in New York plus 1 over the number of people in California. And so I have a 31 over 105, the square root of 31 over 105. If there are 31 successes out of 105, then there are 74 failures out of 105 times 1 over, 71 plus 1 over 34. So I get 0.09513348889. So my test statistic, Z equal X minus mu over sigma. So the difference in the proportions for New York and California. So 15 over 71 minus 16 over 34 minus mu, which is assumed, which here it is equal to 0, divided by the standard deviation sigma, which is 0.951334889. And so you get a negative 2.725860605. So to the nearest hundredth, you have that z is equal to a negative 2.37, negative 2.73. Let's find the critical value. I'll just do it on my calculator. And so find the inverse norm of 1 minus 0.04 divided by 2. So z is equal to 2.053748911. Or if you wanted to do it using your table, you would say, using table 3 here, you would say, well, 0.5 minus 0.04 divided by 2 is 0.4800. And so it's somewhere in between 0.4798 and 0.4803. So 2.05 and 2.06. And so let's interpolate. And so z is equal to 2.05. Well, I just have to do it from here. 2.05 plus 2.06 minus 2.05 over 0.4803 minus 0.4798 times 0.48 minus 0.4798. So 2.054. And so here are my critical values. And here was my test statistic. So my test statistic is in the rejection region. Therefore, I reject the null hypothesis. So no, there is insufficient statistical evidence to accept the claim that the recognition rates are the same in both New York and California. Problem 13. Assume that you want to test the claim that the paired sample data come from a population for which the mean difference is 0. So I have here X and Y. So 510, 28, 410, 47, 512. Compute the value of the test statistic. Round your answer to the nearest hundredth. Hint, the correct test statistic is positive. Oh, so you want it to be positive, so you're gonna have to do an X minus Y. Okay, a Y minus X. I wrote it this way, but I said it the wrong way. A Y minus X, because these guys here are bigger than these guys. So to make it positive, you want to do this minus that. Okay, so the null hypothesis is that the population mean of the differences is 0. The alternative hypothesis is that mu sub d is not equal to 0. Alpha is 0.05. Let d equal y minus x. So let's just subtract. So 10, 6, 6, 3, 7. And so 5, 6, 6, 3, 7. And so let's calculate some of the statistics here. So I have here that the sample mean, sum of all these, 27 over 5, 5.4. Let's look at the sample variance. And so I have 5 of these. I square them, add them up, 155 minus, I add these up, 27 squared over 5 times 4. And so I get 2.3, take the square root of that, 1.516575089. So let's find the critical number. In this case, the degree of freedom is 4. And this is two-tailed. So 4, two-tailed, 0.05. So, oh, I guess I should have also said 4. So I have here that this is two-tailed, 0.05, and degree of freedom is 4. And so I have here plus or minus 2.776. Actually, I should say plus or minus, even though I said it below. So this is plus or minus 2.776. Let's find the parameters. And so the mean for the sampling distribution, the difference two sample means, is the mean of their differences 0 by the null hypothesis. The standard deviation for the sampling distribution of these, the sample average of these differences is, well, the standard deviation, the population standard deviation of the differences, which we don't know, but we can estimate it by the sample standard deviation, which we just calculated, 1.516575089, divided by the square root of the sample size, 5, 0.67823299983. So my test statistic, z equal x minus mu over sigma, well, t equal the sample mean, which we found to be 5.4, minus mu, which is 0, over sigma, which is 0.67823299983. And so I get that t, the test statistic, is equal to 7.961865632. So rounding to the nearest hundredth, it was 7.96. And so we are definitely in the rejection region. So I reject the null hypothesis. So no, there is insufficient statistical evidence to support the claim that the paired sample data come from a population for which the mean population difference is equal to 0. 14, a random sample of 25 women resulted in systolic blood pressure levels with a mean of 95 and a standard deviation of 1.1. A random sample of 61 men resulted in systolic blood pressure levels with a mean of 97 and a standard deviation of 6.3. Use a 0.05 significance level and the critical value method to test the claim that the blood pressure levels for women vary more than blood pressure levels for men, obviously not. Enter the smallest critical value, round your answer to the nearest 10 thousandths. So there is more. So is the variance for women greater than the variance for men or not? So the null hypothesis, the ratio of the variance for women to the variance for men less than or equal to 1. Alternative hypothesis, the variance for women divided by the variance for men is greater than 1. Let alpha equal 0.05. So the degree of freedom for women is 24. The degree of freedom for men was 60. So we have and we're doing 0.05. So 5% points. And of course, it's a right-tailed area. Degree of freedom in the numerator is 24, denominator 60, so 1.70. Let me calculate my test statistic. And so F is equal to, since I'm testing the equality of population variances, then they cancel. So my test statistic becomes easier. It's just the ratio of the sample variances. So 1.1 squared over 6.3 squared, 0.03048626686. So this is not in the rejection region. So we do not reject the null hypothesis. No, there's insufficient statistical evidence to support the claim that blood pressure levels for women vary more than blood pressure levels for men. 15. Dr. Math Prodigy claims that less than 60% of students like mathematics. To test this claim, you decide to ask 10 students, and you find that 2 of them like mathematics. Determine the p-value for this hypothesis test, rounded to 4 decimal places. So the null hypothesis is that the population proportion is greater than or equal to 0.6. The alternative hypothesis is that p here is less than 0.6. Alpha is equal to 0.05. And so we can see that an n here is equal to 10. And x is 2. Well, as we can see here, the sample size is so small, there's no way that the normal approximation is applicable. Therefore, we have to use the exact test. So let's find the p-value. And so I want to find the probability that x is less than or equal to 2. And so this is just the sum r equaling 0 to 2 of, well, again, I'll use the binomial probability formula. So let's use the binomial probability formula. So NCR, so 10CR, P, which is 0.6 to the R, Q, 0.4 to the N minus R, 10 minus R. And so P is just 10C0, 0.6 to the 0, times 0.4 to the 10, plus 10C1, 0.6 to the 1, 0.4 to the 9, plus 10C2, 0.6 squared times 0.4 to the 8th. Again, this is, you can do this on your calculator. Binom CDF 10, 0.6, 2. And so P is equal to 0.01229455536. So P, rounded to nearest 10 thousandths, is 0.0123. Well, 0.0122945536 is less than 0.05. So P is less than alpha, so I reject the null hypothesis. So yes, there's insufficient statistical evidence to reject the claim that less than 60% of students like mathematics. Let me do problem 16. A bag contains 12 marbles. Each marble is either red or blue. You take out 5 marbles from the bag and find that all of them are blue. Test the claim. Determine the p-value and write the answer rounded to 4 decimal places. So let's do that. Well, we're testing, the claim is that 1/3 are red. So success in this case is that you have a red marble. So the null hypothesis is that the population proportion is equal to 1/3. The alternative hypothesis is that P here is not equal to 1/3. Alpha, well, this tells us alpha. So alpha equals 0.05. We don't really need alpha, but for completeness, you need alpha. This is a two-tailed test. I have here that, oh, let me switch this for a second. This two-tailed test, I have here that N, the population size is 12. So capital N is 12. And little n, maybe I should say that, little n is 5. Okay, so the P here, the p-value, is equal to, again, it's a two-tailed test. So I'm going to have to do twice. Well, probability x is less than or equal to 0. Which is the same as x equals 0. But and so I want to do twice the probability. In this case, x is less than or equal to 0. So twice, well, let's see. There are 12 marbles, and I'm choosing 5 of them. So 12 choose 5. There are 4 red marbles, and I chose none of them. And there are 8 blue marbles, and I'm choosing 5 of them. And so you get 0.141414141414. And so the p-value is, rounding near 10 thousandths, 0.1414, which is greater than 0.05. So you do not reject the null hypothesis. So yes, there is insufficient statistical evidence to reject the claim that a third of the marbles are red. 17. To test whether or not there is a significant difference in the average snowfall in Maryland and Virginia, the average snowfall in the 2 states during a random sample of 92 days during a leap year were recorded. In Maryland, the average is 5.4 inches with a standard deviation of 0.5 inches. And in Virginia, the average is 5.2 inches with a standard deviation of 0.4 inches. Test the hypothesis of, I don't like that. Okay, of a 10% level of significance. Use the F test, Walsh's approximation, and the Wilson-Hefferty approximation in the solution of the Behrens-Fisher problem. Use the p-value method. So we want to see if there's a difference, a significant difference or not. So the null hypothesis is that the average for Maryland minus the average for Virginia is 0. The alternative hypothesis, mu sub m minus mu sub v is not equal to 0. Let alpha equal 0.10. We have that the average for Maryland was 5.4. The standard deviation was 0.5, and the sample size was 92. For Virginia, the average was 5.2. The standard deviation was 0.4, and the sample size was 92. So let's conduct our F test to see what formula to use. And so we note here that the variance for Maryland is larger than the variance for Virginia. And so let's try to see if if the population variance for Maryland is actually greater than population variance for Virginia, or if they really were just the statistical fluke and they're actually still the same. They're actually the same. So the null hypothesis is that the variance for Maryland divided by the variance for Virginia is less than or equal to 1. The alternative hypothesis is that the variance for Maryland divided by divided by the variance for Virginia is greater than 1. Now, since we're going from a two-tailed test, alpha equaling 10%, to a one-tailed test, then alpha is equal to 5%. So alpha is equal to 0.05. Degree of freedom for both Maryland and Virginia is 91. So let's try to find the critical value. So let's use the Wilson-Hefferty approximation. So first, let Z equal the inverse norm of 1 minus 0.05. So 1.644853626. You could also let it just equal 1.645, but so A is equal to 2 over 9 times the degree of freedom for Virginia. So 2 over 819. B is 2 over 9 times degree of freedom for Maryland, 2 over 819. So C is equal to B, Z minus 1 minus B squared, negative 0.9885150,148. B is equal to 1 minus A times 1 minus B, 0.9951219,585. A is equal to A times Z squared minus the quantity 1 minus A squared. And so you get negative 0.9885150,148. So F is equal to a negative B plus a sign of AZ, which is negative, so minus the square root of B squared minus A C, all divided by A cubed. And so F is equal to 1.414333531. So let's calculate our test statistic for the F test in order to see what formula. Again, we're trying to see what formula to use. So F is equal to, since we're testing the equality of population variances, then the test statistic is just the ratio of the sample variances. So 0.5 squared over 0.4 squared, 1.5625, which is greater than that. So we are in the rejection region. And so we're in the rejection region. So I reject the null hypothesis. So I rejected the null hypothesis. So the variances are not equal. Therefore, we will use the unpooled formulas. So let's try to determine the critical value for my t-test. Well, first let's find my degrees of freedom. So let's figure out my degrees of freedom. So let's use Welch's approximation. So alpha equals the variance, sample variance for Maryland divided by the sample size for Maryland. So 0.5 squared divided by 92, 0.0027173913. Beta, sample variance for Virginia, 0.4 squared divided by the sample size for Virginia, 92, 0.0017391304. And so my degrees of freedom is just going to equal alpha plus beta squared divided by alpha squared, degrees of freedom of Maryland, which is 91, plus beta squared divided by degrees of freedom for Virginia, which again is 91. So we get 173.63333712. So let me figure out my parameters. The mean for the sampling distribution of difference of the sample means is the mean of the difference of the population means, which by the null hypothesis is assumed to equal 0. deviation, the distribution example is we will estimate it by the sample. And again, we don't know that. We'll approximate it by the sample variance for Virginia over the sample size for Virginia. 0.06675718141. So let's calculate my test statistic. Z equal X minus mu over sigma. So T is equal to the difference of their sample means, 5.4 minus 5.2, minus mu, which is 0, divided by sigma, which is 0.0667571849. And so I get 2.995932202. So let's calculate the p-value. So p is equal to the probability that t is not equal to this, with degree of freedom this. Okay, so this is actually a right on the right. This is a right tail. So let's do 2 times the probability that t is greater than 2.995932202. Well, it didn't say that we couldn't use a TI-84, so let me just use a TI-83. So again, you could do a you could use the approximation formula for T, and then approximate it by Z, and then you could look at your normal table using linear interpolation. But we've already done that, so I don't need to do it again. So this will just be 2 times, and rather than going from negative and from that 2.99 to infinity, I'll just do 0.5 minus the middle. So 0.5 minus TCDF. I'll start at 0. I'll end at 2.995932202, comma, my degree of freedom, 173.63333712. And so I get 0.003136597. This is less than 0.05. And so, let me just see for 1 second. Yeah, it was 0.05. This is less than 0.05. So we reject the null hypothesis. So yes, there's insufficient statistical evidence to reject the claim that there is a significant difference in the average snowfall in Maryland and Virginia. 18. A manufacturer considers his process to be out of control when he detects when defects, no, that is actually correct. A manufacturer considers his process to be out of control when defects exceed 4.9%. In a random sample of 134 items, the defect rate is 10%, but the manager claims that this is only sample fluctuation, and production is not really out of control. At the 10% level of significance, use the p-value method to test the manager's claim, enter the test statistic, round your answer to the nearest 100. So the null hypothesis is that the population proportion is equal to 4.9%, 0.049. The alternative hypothesis is P is not equal to 0.049. Let's use the level of significance of 10%, so alpha is 0.10. N was 134, and the sample portion was 0.10. So let's see if the normal approximation is applicable. The answer is just barely. Look at n times p, 134 times 0.049, 6.566. It's just barely greater than 5. N times q. By the way, the latest, so currently right now, sociologists and all that are using 10 rather than 5. So if you're using the value of 10, this actually wouldn't be acceptable. N times q, 134 times, well, if I have a 0.049% chance of success, I have a 0.951 probability of failure. So 127.434. Well, that's certainly greater than 5. So I can use the normal approximation. So let's look at z, and z for 10%. So 10% one-tailed, z value is 1.282. So this is my rejection region. Okay, so let me determine my parameters. So the mean for the sampling distribution of all possible sample proportions is the population proportion, which by the null hypothesis would be 0.049. The standard deviation for the sampling distribution of all possible sample proportions is the square root of PQ over n. Well, 0.49, so the square root of 0.049 times 0.951 divided by 134. And so I get 0.0186481562. So my test z x minus mu over 6, 0.049 divided by 0.0186481562. So I get that z is equal to 2.73485482. And so my test statistic round to the nearest hundredth is 2.73. Oh, it says to find the p-value. So the probability that z is greater than 2.73485482. Again, let me do 0.5 minus normal CDF from 0 to 2.73485482. And so I get p is equal to 0.00312.04439, which is less than 0.10. So p is less than alpha. Therefore, you're in the rejection region. So you reject your null hypothesis. So no, there's insufficient statistical evidence to support the manager's claim that this is only a sample fluctuation and the production is not really out of control. 19. Researchers conducting a study to determine whether magnets are effective in treating back pain. The results, higher values indicate larger reductions in pain levels, are shown in the table for the treatment with magnets group and the sham or placebo group. So we have here for the treatment group, sample size 19, mean 12, standard deviation 4. For the sham, sample size 22, mean 10, standard deviation 3. Assume that the two samples are independent, simple random samples selected from normally distributed populations, and do not assume that the population standard deviations are equal. Use the p-value method and a 0.10 significance level to test the claim that the treatment mean measure of reduction in back pain is equal to the sham mean measure of reduction in back pain. Hint, consider the statistic treatment minus statistic sham. enter the test statistic, round your answer to the nearest thousandths. This was just telling you which one to do, so we have the correct sign. So the null hypothesis. The mean, the population mean for treatment minus the population mean for sham is 0. Alternative hypothesis. Mu sub t minus mu sub s is not equal to 0. Alpha is equal to 0.10. So let me just rewrite what we had from before. So for treatment, the average 12, standard deviation 4, sample size 19. For sham, average 10, standard deviation 3, sample size 22. We're assuming that the variances for treatment and for the sham are not the same, because it said there to. So you're assuming that, so do not assume that they are equal. So we're not assuming that they're equal, meaning that they're not equal. Since they're not equal, then we're going to have to use the unpooled formulas. So let's do Walsh's approximation. So let alpha equal the variance, the sample variance for treatment 4 squared divided by the sample size for treatment 19. So 0.8421052632. Beta is the variance for the sham 3 squared over the sample size for the sham 22. 0.409090909090. So the degree of freedom is alpha plus beta squared divided by alpha squared over the degree of freedom for treatment, which is 18 plus beta squared divided by degree of freedom for the sham, 21. So I get 33.05093338. Let me determine my parameters. So the mean for the sampling distribution, or the difference of these two sample means, is the difference in their population means, which by the null hypothesis is assumed equals 0. The standard deviation for the sampling distribution, or the difference of these two sample means, is the square root of the variance for treatment, which we don't know, but we'll approximate it by the variance for the sample variance for the treatment over the sample size for treatment, plus the population variance for the sham, which again we don't know, we'll approximate it by the sample variance for sham divided by the sample size for the sham. Well, this is just alpha, and this is beta. So we'll just do alpha plus beta, and then take its square root. And so I get 1.118568805. So let's determine my test statistic. So T, so Z equal X minus mu over sigma. So T is equal to the difference in their sample means. And so 12 minus 10 minus mu, which is 0, over sigma, which is a 1.118568805. So I get 1.787999085. So rounding to the nearest thousandths, I get 1.788. So let's calculate the p-value. This is a two-tailed test. So it's two-tailed. So it's a probability that T is not equal to 1.787999085. So twice
the probability that t here is greater than this. So let's just double the right tail. So 2 times 0.5 minus t CDF. I'll start at 0, comma. I'll end at 1.787999085, comma, my degrees of freedom, which we found 33.05093338. And so I get 0.0829481998. That's less than 0.10. So since p is less than alpha, we have that it's in the rejection region. So I'm going to reject the null hypothesis. So no, there's insufficient statistical evidence to support the claim that the treatment mean measure of reduction in back pain is equal to the sham mean measure of reduction in back pain. 20. The table below shows weights of 7 subjects before and after following a particular diet for 2 months. So before 155, after 155. So before 154, after 151, 154, then 155, 155, then 153, 151, then 151, 155 stays 155, 150 gained and to 152. So using a 0.05 level or is negative. Use the critical value method of hypothesis testing. Enter the smallest critical value, round your answer to the nearest thousandths. So is greater than 0. The alternative hypothesis, mu sub d is less, and alpha here is equal to 0.05. So let's do after minus below, after minus before. And so you just subtract 0, -3, 1, -2, 0, 0, 2. So 0, -3, 1, -2, 0, 0, 2. So let's find some statistics. So let's find the mean. Let's add these all up. -2 divided by how many there are, 7. So negative 0.285714285714285714. So the variance for the the sample variance for these differences is, well, n, which in this case is 7. Oops. 7 times, well, the sum of their squares, 18, plus, well, their sum, -2 squared, divided by, well, 7 times 6. And so you get 122 over 42. So take the square root of that. So you get a 1.704336206. The degree of freedom here is 6. And this is left-tailed, 0.05. So left-tailed, or one-tailed, 0.05, degree of freedom 6. So a negative 1.943. Let's determine my parameters. So the mean for the sampling distribution of these average differences is the mean of the differences, which is assumed by the null hypothesis equals 0. The standard deviation for the sampling distribution of the difference of these, the average of these sample differences, is the population standard deviation of these differences, which I don't know, but I can approximate it by the standard deviation, which we just found found. Let's calculate my test statistic. So z equal x minus mu over sigma. So t is equal to the sample mean, which we found was -2, minus mu, which is 0, divided by sigma, which is 0.6441785361. And so t here is equal to a negative 3.104729,338, which is in the rejection region. So I reject the null hypothesis. So yes, there's insufficient statistical evidence to reject the claim that the diet is effective in reducing weight.